Hello, this is Mark Armitage speaking to you from the microscopy facility in the biology department at California State University, Northridge. We welcome you to this series of videos. The purpose of these videos are to train you in microscopy in general, but on confocal microscopy in specific. And so behind me here you see the Leica SP5 confocal microscope. You're going to be learning how to use this instrument to do your experiments in confocal microscopy. We want to thank the Keck Foundation for their funding for these videos. They supplied the funding to pay for us to produce these videos for you. You'll see the screen behind me which has text on it, and you will be noticing some figures on that monitor. Those figures are courtesy of Nikon Microscopy University. And it's a wonderful website. If you Google Nikon Microscopy University, you'll find a whole host of interactive tutorials and other information related to microscopy. So we want to thank them for allowing us to use their figures during this presentation. Now, this is a very complex instrument. There's a lot of technical aspects to it, and so what we'd like to do is to begin with a standard compound microscope for fluorescence. And so we're going to be going to another microscope to show you the basics of microscopy before we come back to the Leica SP5. We're going to begin our discussion of microscopical principles by using a standard compound microscope. Now, you're probably familiar with dissecting microscopes, which you've used in some of your labs to dissect organisms or other things. That's a very low power magnification instrument, and this is a different instrument. This is called a compound microscope. The reason this is called a compound microscope is because to get the resultant magnification out of the instrument, you multiply the magnification of the objective lens times the magnification of the eyepiece lens. Ergo, this is a compound microscope, and there's other features that we're going to discuss as we go along. Useful magnification for an instrument like this is about 2 power up to maybe 1200 power. You really can't go any higher than that and still maintain the resolution that you're looking for in a microscope. So let's begin with some basics, and you'll see a figure that I have here on the screen. And in this figure you'll see yellow coloring, and that indicates the light path, and we'll be discussing how the light path travels through the compound microscope, and I'll be referring to this figure again and again. But let's begin over here with the microscope. Built into the stand in the base is an illuminator. An illuminator supplies light to the microscope. In this case, we have a tungsten halogen illuminator built into the base with a tungsten halogen bulb that burns very bright and very white. And that light travels from the bulb and the lamp housing up to a right angle mirror in the base, and then it comes vertically through the field diaphragm of the microscope. The field diaphragm is important, remember, because when we close it down, we can see it in the field of view, and it's also important for alignment. We'll show you how to perform that alignment in another section. The light travels through the field diaphragm and comes into the condenser. The condenser is an optical apparatus that does just as its name suggests. It condenses the light into a fine cone of light so that it can travel through the specimen on the stage and then into the objective. Each of these is an objective. Each one is highly corrected for the magnification that it produces and the resolution. We'll be discussing that more later. Then the light travels through the objective where all the useful magnification takes place. It goes into the nose piece, and you rotate the objectives by holding the nose piece on the knurled rubber band. It travels through the nose piece and up into the head of the microscope. This is called a trinocular head because you have 2 eyepieces for viewing and a third port to which you can attach a camera. Historically, we've used film cameras on the trinocular port, but nowadays, with the advent of digital microscopy, we can put digital still cameras on the microscope, or also video cameras which record live motion in living cells. We also have binocular tubes, and you may have seen monocular tubes in the past, but this one's called a binocular tube or head. We also want to discuss the illumination coming from above. We have transmitted light illumination through the microscope, and we also have reflected light illumination. In fluorescence microscopy, we use reflected light illumination. So let's discuss the components of the reflected light illuminator. Here we have a large lamp housing which holds a bulb that burns very brightly. Typically these are called mercury vapor pressure bulbs. These are high pressure bulbs that must be handled very carefully because they can explode and destroy your lamp house. And this puts out a tremendous amount of illumination. We'll look at a graph on the screen later that shows you what's called the emission spectra. The amount of information or light put out by this bulb is a very high amount of light across a varying number of wavelengths. And that's important because when we do fluorescence microscopy, we have to use different colors to illuminate our specimen. We'll discuss more about this later. But the light travels from the lamp house through the vertical illuminator. It goes through an excitation filter, which is a specific color that's used to excite our fluorophore, which we'll discuss more about later. And you'll see this color in a second. It goes through the excitation filter, then it hits a mirror and is reflected downward to the specimen. So this is reflected light hitting our specimen. Then the light that is emitted from our specimen travels back through the objective, through the mirror, which passes it to the binocular or trinocular head. So if I push a set of filters into the light path, you'll see the bright blue light. What is this light? This is about 490 nanometers of light that it's being used to excite our specimen. We'll discuss more about excitation and emission later. But the light that comes off the specimen, or the emission light, travels through the objective and to the observer's eyepieces. This is very low light, and therefore you will often see a fluorescent microscope used in a dark room. Now we're going to go to the diagram and show you these features on the diagram as well. In order to understand these concepts a little more clearly, let's refer to the diagram of the microscope that we have on the screen. Here you see the compound microscope with the transmitted light illuminator. So we have a tungsten halogen bulb in the transmitted light illuminator that sends light through the base of the microscope. Here you see it traveling through the field diaphragm. And remember that the field diaphragm is the diaphragm that we can close down and see it in the field of view. That's why we called it a field diaphragm. The light then travels through the field diaphragm and is reflected off a right angle mirror, and it leaves the base. It leaves the base of the microscope, and now it travels into the condenser. Remember, the condenser is an optical device that condenses the light into a small cone of light so that it can travel through the specimen, which is here on your XY stage, and into the objective. In the objective, all of the useful magnification takes place. This is where all the high-resolution images are formed. Those images are then projected through the nosepiece and through this vertical illuminator, which we'll talk about in a second, and into the binocular or trinocular tube for the observer to see. So that's transmitted light. Now this microscope also does reflected light. Remember, in fluorescence, we're using reflected light to illuminate our specimen. So this is the fluorescent vertical illuminator. Here we have the lamp housing, which has that mercury bulb that we're going to discuss more in a few minutes. It produces a lot of light which travels through the vertical illuminator. Here you can see it traveling through a field diaphragm. Again, we can close this diaphragm down and align it for alignment purposes. The light then travels through what we call a barrier filter. An excitation filter that produces the light, that blue light that you saw in the microscope, to excite our specimen. Now, a lot of specimens will autofluoresce. You can excite them with a bright light like 490 nanometers, and they will automatically give off light or emit light. That's called emission light. Usually the emission light is a longer wavelength than the excitation light, and we'll talk more about that later. So the light travels through this excitation filter, reflects off of a mirror, and is sent down through the objective to impact our specimen. So we're reflecting light off of our specimen. Now the light that is emitted from our specimen travels through the objective, through the nose piece, through the mirror, and up into the trinocular tube where the observer can see it, or we can record it on film. That's reflected light fluorescence microscopy. While you're working with a Leica confocal microscope, you're going to be working with some very expensive objectives. Some of these objectives are about $10,000 each. And so it's very important that you understand the particular specific qualities of each objective. And we're going to do that by concentrating on information that's printed right on the barrel of the objective. Now, to do this, we're going to go to a diagram on the screen, and we'll be discussing all of these things that are printed on the barrel of each objective. You'll see on this screen here a 60x objective and a cutaway. Now, the first thing that I want you to notice is all of the lenses that are inside the objective. These individual lenses are used to correct for several different aberrations that are caused when we produce glass for magnification purposes. We're going to talk about those aberrations in a few minutes. But first, let's just talk about the information that's printed on the barrel of the objective itself so that you can understand what these things mean. The first thing you see on the objective, of course, it's a Nikon objective, but we'll be working with Leica objectives on the microscope that we're using. There's a description of the type of lens, plan apo. We'll discuss that again in a little bit. But more importantly, the magnification of the objective. Here it's printed 60x or 60 power. Now you're going to be working with a 20x objective. You're going to be working with a 20x wet objective. So we'll have to talk about oil immersion and other immersion. You'll be working with a 63x, again, wet objective. And you'll understand what I mean by wet in a few minutes. And also a 100x wet objective. So here we have a 60x objective, and then it has a slash, and next to the slash it has a number 1.40. That number 1.40 is called the numerical aperture of the lens, or the objective. Numerical aperture is a designation of the light gathering capability, or the strength of the objective in producing a very well lit high resolution image. And you'll understand more about numerical aperture in a minute when we discuss that more. But numerical aperture is very important. In order to achieve the actual numerical aperture that's printed on the objective, your microscope must be perfectly aligned. The condenser that we talked about has to be in the perfect vertical position. We're going to cover all this in detail. But you cannot just throw a specimen on the microscope, throw the objective in the light path, and get that maximum numerical aperture out of the objective if you're not doing all the steps that are required to achieve that. So numerical aperture is very important, and we'll talk about that more in a second. You also see the printing, it's a little hard to see here, but oil. Some objectives use what's called an immersion oil. And so you have to put a drop of oil in between the front lens of the objective and the cover slip on the slide that you're looking at. Some objectives use glycerin. Others are called water immersion objectives. We have objectives on the Leica confocal microscope that use all three of those. So we'll discuss those as we go along. Now you also see some other numbers here on the barrel of the objective. One is the little infinity sign. This brings up the topic of tube length. What is tube length? Tube length is the apparent distance that you see the image that you're looking at. It appears to you to either be at a distance at which you would hold a book to do reading. That's called 160 millimeter tube length, because the book is 160 millimeters from your eye. That's one form of tube length. Most of the newer objectives are infinity corrected. So instead of having a fixed tube length where you would hold a book at 160 millimeters, you're now looking at an image that appears to be coming to you from infinity. That's important because all these objectives from the different manufacturers can be screwed onto the different microscopes, but they're not always compatible. We have an infinity optically corrected system on the Leica confocal microscope. So you cannot use objectives that say 160, and they would say 160 right here. This one says infinity. So we have to use all infinity objectives. There's also another very important number right next to the tube length, and in this case it's 0.17. That is the thickness of your cover glass. Again, in order to achieve the highest numerical aperture from your objective, you must use a cover glass of 0.17 millimeter thickness. Now this can be confusing because some manufacturers sell cover slips that are labeled number 1 or number 2 or number 1.5. How do those numbers relate to the number that's painted onto the barrel of my objective? Well, a number 1 cover slip is about a 0.14 to 0.15 millimeter thickness. A 1.5 cover slip is a 0.17. A number 2 cover slip is a 0.19 or a 0.20. That's a little too thick. And so you might have in your laboratory a box of cover slips that's labeled number 2. Those are too thick. You should use a number 1.5, which is a 0.17 millimeter thickness on your cover slip. The reason this is important is because all these lenses that are built into the objective are designed for use with a 0.17 thickness cover slip. So your maximum resolution will only be achieved with a 0.17 millimeter cover slip. The other thing that's important when you're making your slides, you're either going to be working with thick sections of tissue or very thin that have been thin sectioned. What's important is not so much the thickness of your specimen, because a confocal microscope can accommodate a fairly thick specimen, but the mounting medium that you use to glue that cover slip in place is also very important because of a thing called refractive index, and we'll talk about that also. So make sure that you're using the proper mounting medium to mount your specimen and your cover slip to your slide. It's also a good idea to compress the cover slip a little bit if you're using a mounting medium. If you're working with cells that are in an aqueous medium, then that's different. You don't have to compress that as much. But if you're working with a specimen that requires a mounting medium, compress that cover slip down a little bit and you'll get higher resolution images. Another feature that's important for you to note on the Leica confocal microscope about the objectives has to do with the protection of the objectives and your specimen. Most high-quality objectives have a spring-loaded front element so that when you push on it, it actuates against the spring and then comes back into place. Now this is to prevent any damage if you were to run your objective up into your slide. This is not a license for you to run your objective up into the slide. It's just a prevention measure that's used to prevent the breaking of your slide or of your specimen or harming these very expensive objectives. So be aware that they are spring-loaded. Another feature that's important on the objectives that you'll be working with, particularly the 63x objective and the 100x objective, is that you can compress the front of the lens down and rotate it, and it locks down and out of the way. This is very useful if you're rotating the nose piece and you don't want your objective to make contact with your slide or something on the stage. So remember that you can lock them down and out of the way. A third feature on the objectives that you're going to be working with is very important, is that they have a correction collar. Some of them have a collar that you can turn on the objective that corrects for differences in the cover slip thickness, and also it corrects for the different kind of immersion liquid that you use on the objective.